Welcome back to the Art of Math, to another tricky algebra video. We're going to go over finite and infinite geometric sums. So to recap a little bit, we've seen problems such as this: 4 plus 7 plus 10 plus 13 plus 16 all the way up to 85. And these are called the arithmetic series. Arithmetic just means that the difference in the terms is always plus the same number. So this is plus 3 plus 3 plus 3. And if you go to video number 37, we'll go over how to do that in that video. Now, in this video, we're going to go over geometric series. So the geometric means instead of moving by plus 3 plus 3 plus 3, we're going to be moving by multiplying. So it's going to be plus, you'll see in this example, for example, we have 5 plus 5 thirds plus 5 ninths plus 5 27ths plus all the way up to 5 over 3 to the 40th power. So how do we get each of these terms? Instead of adding the same number, we're going to be multiplying 5 by a third, this by another third, that by another third, everything by another third. So that's finite because we end on a specific spot. There's only a finite amount. However, there's also the infinite geometric series, and this is related to the old Greek paradox, Zeno's paradox, of if I walk halfway towards a spot and then a quarter of the way, and then an eighth of the way, and then a 16th of the way, having my number every time, and I keep doing this infinitely, so that dot, 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 notice there's nothing at the end. The question is, will I ever reach 1? Will I ever cover the whole distance? So these are two sort of really good problems that demonstrate both the finite series and the infinite series. And we're going to go over how to calculate these. So first of all, let's make this very general and not specific numbers. So we're going to introduce A and R. So A just means that's your first term. So 5 is your A. R is going to be your ratio, so that's going to be your 1/3, because every time to get the next term you multiply by 1/3. So we can represent this problem by A plus AR squared plus AR cubed plus dot, 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 all the way up to A times R to the n minus 1. Now, why did I pick n minus 1 and not n? N means the number of terms. Notice in this example, we have the 40th power here. So we start with 3 to the first. So that's 40 terms here, but here's your 41st term, which is your 5. So if you want to make this an n, then you'll have n plus 1 terms, and then that's kind of ugly. So I'd rather have the total number of terms be n, which is a nice number, but the trade-off is this is an n minus 1, which is a little convoluted. Okay, so we're going to just assume this is n minus 1. Same thing for the infinite, except it goes on forever. So the beautiful technique in this video, which is going to be very similar to what we've already seen with puzzle pieces and reusing puzzle pieces, is all we're going to do, this may seem like a really stupid thing, one of the big insights is we're literally going to give this a name. We're going to call it S for the sum. That may seem like not a big deal, but why is that such a powerful thing to call this S? That means we can refer to that whole thing without always having to write it, and now we can just work with the S. So that's sort of the first insight. The second insight is we're going to copy and paste our S. However, we're going to do something a little clever. We're going to tweak it. We're going to multiply our S by an R. What's the point of doing that? We have a ton of ugly stuff which we don't want to manually add. So how do you kill off a lot of ugly things with a lot of other ugly things? So that's what this RS is. The RS, now if we had just made this another S and we subtracted S minus S, we would get 0. Everything would cancel out. So we don't want everything to cancel out. So the R shifts everything. So now the A is multiplied by the R, that's AR. AR turns into AR squared. AR squared turns into AR cubed. So everything's stepped up by an extra R. So that AR to the n minus 1 becomes an AR to the n. Now, why is that so important? If you remember from our telescoping video way back, when we subtract this, if you notice diagonally, everything repeats. So the only things that are going to be left are this upper left corner and this bottom right corner. So when we subtract these, we'll have S minus RS, and these will annihilate all the diagonal terms. So the A will stay, and so will the AR to the N. So this is very nice. Now all we're going to do from here, this is the key step, by the way, right? So we've killed off almost everything. We only have 4 terms left, which is very nice. We're going to factor out the A on the left and the S on the right. So that's where we get this. A times 1 minus r to the n. That's just this left side rewritten with a factored out a. And then the s minus rs becomes s times 1 minus r. So we just factored out that s. Now we're interested in what is the s. So we're just going to rewrite the right side on the left side. So that's why the s is here. And s equals this left side, a times 1 minus r to the n, all over 1 minus r. So again, to recap, a is your first term, n is the number of terms, and r is the ratio. That's the multiplier between terms. So this is the formula. So if you have any examples, so I'm just going to run you guys through this original example. Our first term was 5, and our ratio was 1/3. So if you plug this 1/3 to the 41st into a calculator and crunch this, you should get a number that's approximately 7.5. It's actually that number, but I just rounded it here. So this may seem a little maybe strange, but if we go back to the original problem, you may think like, hey, 7.5 is way too small for all of this stuff. But remember, it's decreasing. So although we're adding 5 and then 1 2/3, we're very quickly adding less and less. So it makes sense that the whole sum would not blow up to be a huge number. So now that we've done that, we're going to cheat a little bit, and we're going to derive the formula for the infinite series. So by cheat, I mean we're just not going to have to redo our work. So if we go back here, we have a times 1 minus r to the n divided by 1 minus r. So what does it mean when it's an infinite series? It means the n, the number of terms, is infinite. So remember, our r is some fraction. So in our example, it was 1/3. So if you take a fraction such as 1/3 and raise it to the infinite power, it keeps getting smaller and smaller. So it's 1/3 times a third times a third times a third. It's going to go to 0. Now, you may think like, well, what if r is not a third? What if r is like 7? Well, in that case, the sum will be infinite because you keep adding larger and larger terms. So for this to make any sense, the terms have to be shrinking so that it converges to some sensible number. So remember, if you take any fraction, a half, a third, 2/3, whatever, and raise it to the infinite power, it's going to shrink down to 0. So what does that mean? That means we can just ignore this r to the n term, so that's going to be gone, and 1 minus 0 is just 1. So this formula is going to simplify to this much nicer formula. So notice this right part just dropped out, and we just have s is equal to a over 1 minus r. So let's run our original example with the 1/2 plus a quarter plus an eighth. So our first term is a half. Now what's the ratio? It's a half because we went from a half to a quarter to an eighth. So if you crunch this, you'll get 1. So that means indeed in the original problem, this sum will approach 1 if you do this infinitely long. So if you have an infinite amount of time, you just keep doing this, eventually you'll get there. All right, except not in a human amount of time. All right, so in that covers basically how you find the sum of a finite geometric series and an infinite geometric series. So I encourage you guys to pick different numbers and apply these formulas, go over the derivation again, and make sure this feels good to you guys. One last note. So I've been a little bad about this, so I want to make a point of it in this video to read and skim the descriptions to the videos right below the videos, because I often put additional things, whether they're to clarify the video or extra things to explore beyond the video. So you may want to go revisit some of the old videos you've seen, and sometimes I'll even do it much later after the fact. I try to do it in real time, but sometimes I'll come across new stuff and I want it to be more complete. So just make sure you're not totally skipping the descriptions because you might find them useful. All right, see you guys in the next video.